All right, here we go. Part 2 here for the space unit. We're talking about 9.2 in your textbook, and that's gonna run us. Let's see, about page 314 in your textbook that you're using here now, Pearson Sask Science 9. If you're on that textbook, you can go to page 314. So the Earth is in motion. I'm not sure if you guys knew this. We've talked about this. The Earth is in motion. The Earth is revolving and rotating. Okay, so the rotating is rotating on its axis, so it's spinning. So when we say spinning, that is rotating, and revolving is when the Earth actually travels in orbit around the sun. So what do our notes say here? The sun appears to travel across the sky during the day because the Earth spins on its axis. Okay, so let's see if I can do this here. I'm gonna, try and go to my my full screen here. You guys can't see that, but this should be full camera on me. So this is the Earth, and I've got this little pen doohickey here extending through the center of the Earth. This is the extension of the axis that goes right through the middle. And the Earth spins like this, okay? It spins. That is rotating on its axis, okay? It rotates like this. And so, because this is us right about here, okay, that little dirty spot there, that's us. We're near the top. So when we spin like this, I'm looking out. We're looking out here, looking out, looking out. When the sun is sitting over there, it appears that the sun is moving across the sky. So this is what it looks like. It looks like the sun's going across the sky, but really the sun's staying still, and we're spinning on our axis so that the sun looks like, hey, it's rising, it's midday, and then we're over here, we're looking over here, and now the sun goes down. But we're just facing the other way. Sun's over there, we're facing this way at night. You see that? So sun doesn't move so much, we spin. Now revolving is when the Earth is going around the sun throughout the year. Okay, so it spins around the sun, or not spins, revolves around the sun. So the Earth is going like this as well as spinning. You see that?
Doesn't the sun move a little bit?
Oh yeah. I think I hit the wrong button there. I think the galaxy is our spiral galaxy. We'll talk about that a little later. It's spinning. Yeah, so the solar system is a tiny little speck inside of our big galaxy. The galaxy is moving a little bit. The solar system is moving along with it. Everything is relative, right? Because the Earth is spinning at thousands of miles an hour right now. Yeah. We can't feel it. We don't know, right? It feels like it's pretty rock solid right now, but it's actually moving. So it's all relative, right? Right now, you and I, you're not moving because you're sitting in one spot, but you're just not moving compared to me. If someone was driving by in a car, you would look like you're moving. You're over there. Oh, now you're over there. Now you're over there. See ya. Because I'm driving a car. So it's all relative.
That's
yeah,
like
it's
the
train thing. Yeah. Okay. All right, so in these pictures that you have in your notes here, okay, so you can see that the axis goes through the center of the Earth. One day is one rotation of the Earth around the axis, okay? So when we're facing the sun, it's daytime. When the Earth spins around, rotates, and we're over here, it's nighttime. And then over here is when the sun starts, coming up, right? Or whatever. Over here, the sun is coming up. And the Earth's seasons, we talked about this the other day, about solstices and stuff like that. But when we're on the northern hemisphere, so when we're over here on the top, this is winter because we have fewer hours of sunlight. The sun is less direct, it's lower in the sky, so a lot of those sun rays kind of deflect off and they don't actually penetrate us and that sort of thing. In the summer over here, when we're faced towards the sun, it's more direct light, it's more hours of sunlight and so on. Consequently, it's opposite for people in the southern hemisphere. I think you might have heard that. But like in Australia, right? When it's coming to winter in Australia, when it's coming to winter here for us, it's becoming summer in Australia. So it's really hot because it's opposite for them. See, they're facing towards the sun. Down here, they're facing towards the sun. Yeah, so those places in the southern hemisphere have opposite seasons as we do.
Isn't that like Africa, when we have night, they have day?
Yeah, if they're on the opposite side of the world, then when it's nighttime here, it's daytime there, and so on. Yeah, so seasons are opposite, days are opposite. Yeah. For us, if they were directly, if we could look down, right, directly through the center of the Earth right now, whoever's on the exact opposite side would have the exact opposite situation as us. It would be, if it's daytime here, it's nighttime there. If it's winter here, it's summer there, that kind of thing. Okay, 23.5 degrees. We talked about the tilt of the Earth. Let's continue talking about this. The tilt of the Earth is perfectly aligned for life. First of all, this is actually a very this is a widely underestimated special thing that the Earth was created to sustain life in a really cool way. And one of the things, just one of the many hundreds of things that we could think of that makes life special for Earth, makes life special for Earth, or Earth special for life, is the tilt of the axis of the Earth. It's exactly 23.5 degrees, and that is helpful for our survival in many different ways. But we'll talk about a couple since we're talking about seasons and days and heat and stuff like that. So the tilt of the Earth is perfectly aligned for life to exist on Earth. If the tilt were too extreme, so we were faced too far, towards the sun, in a sense, or too far away from the sun, the seasons would be way too extreme for things that were not on the equator. Now, the equator wouldn't change much throughout the year, still wouldn't be comfortable, but so think about us in the summertime. If it would get a lot hotter in the summertime for us, and it would get a lot colder in the wintertime for us if the tilt was different like that, just even considering hours of sunlight and stuff. If the tilt were too small, so if the tilt of the axis was closer to 90 degrees perpendicular from the direct line from the Earth to the sun, or if it was more straight up and down, okay, then the equator would just get boiling hot. It would just get hot. It would be pretty hot, and the poles would be cold all year round. So just it would be like winter compounding winter, and then the next season would be winter, the next season would be or whatever for us that are closer to the poles. Right? Because remember, it's the tilt of the axis and the time of the year that changes our general weather pattern. So if the tilt was changed even slightly, I mean, it would be super cold. Probably wouldn't be able to live on the north of where we live now, like north of the tropics, probably there, the Tropic of Cancer, south of the Tropic of Capricorn, whatever that is. Like we talked about the other day. So if you live too far north, it would be just uninhabitable. We'd all have to live closer to the equator to survive. Also, another thing, the tilt is perfect to balance the moon's orbit and many other fine-tuned aspects of life. Okay? So there's a lot of things that are tied to the tilt and the axis of the Earth. So we should be pretty thankful that the Earth is tilted at 23.5 degrees. All right, Earth's orbit. So we talked about the Earth rotating, that is spinning on the axis, but we also talked about the Earth's revolution around the sun. The Earth's orbit is slightly elliptical. So if you look at this little diagram right here, this is the path of the Earth's orbit. It's not a perfect square. It's a little bit flat, and this doesn't do it quite justice. It looks like it's a perfect circle here. I'm not sure what it looks like on the screen up there. But it's slightly elliptical, and the sun is not directly in the center. It's not in the very middle. The sun is off-centered just a little bit. How do we find this out? Just different calculations, throughout the year, measurements, that they can do with telescopic equipment and things like that. So there is, the Earth is a little bit further away from the sun at certain times of the year than others. The path is almost a perfect sphere, but not quite, or that should be circle, actually. If the orbit was more elliptical, then life wouldn't exist as we know it on Earth. Okay, so if it was flatter, if we were further away from the sun for most of the year, it would be not good. And it's just right. We get cold in the northern hemisphere. In Canada, we get pretty cold in the winter, pretty warm in the summer. But any difference in these orbit paths or tilts of the axis, things like that, would really, really mess things up. It would really mess things up. Okay. Guys doing good? Yeah. All right, the moon, a satellite, is any object that orbits a planet. Our moon is a natural satellite. So you've heard about satellites, TV, radio communication, cell communication, all that sort of stuff. These are man-made satellites that we put in orbit. So we basically fire them off at a rocket and let them float up in space. And we put them at a certain position so that they would orbit the Earth and they would keep in their orbit. So we won't talk too much about orbits and satellites, but it is possible, obviously, for us to put satellites into space so that they would travel around the Earth and be useful for communication and stuff like that. Satellites used for TV. Now here's the interesting thing. Satellites used for TV are at a certain position where they rotate around the Earth. Let me see if I can get this here. So if we're using satellites for TV, so here's the Earth, here's us maybe. And if we have a satellite right here, I'm going to try and just draw a little satellite here. Okay, satellite's floating around. It is traveling, around the Earth like this. Whoops, let's go this way. It's traveling around the Earth like this, okay, in a circular path, at the same rate, really, that the Earth is rotating. Okay, so that it's always in the same position, just like the Polaris star. This satellite is moving around so that when we look up at the same spot, this satellite is always at the same spot because it moves around with us. As we move here, we look up and it's here. It's always at the same spot. Wherever we are, it's always at the same spot when we look up in the sky. And so that's pretty cool. And that's why when you tune satellites, and I don't know if anybody does this anymore, but back in the day when you had the satellite dishes, on the side of your house and you had to position them, it was pretty fine-tuned, but there was a satellite out there in space that we couldn't see, but we had to point that dish right at the satellite to get good reception. And we didn't have to adjust that every hour because that satellite was always in the exact same position according to, from our perspective, right? Because it would always move at the same rate as we move, and so we could always and so it's very reliable to, bounce signals off these satellites, and here we go, and that's no problem. And when we move over here, you can still bounce the satellite, and it's always very predictable. So it's kind of like if you stick your arm out right now and you twist your body, twist your torso, the end of your finger is always at the same distance away from your shoulder, right? Okay? And that's where the satellite would be. So when you rotate around, the satellite is at that position at the tip of your finger, and it's about that far away, and it's rotating at that speed so that it matches the rotation of your shoulder.
That's what they're doing with.
Okay, so our moon reflects light of the sun at night. It does not produce its own light. I think you guys know that. And the reason why we have the phases of the moon is because we can see the sunlight on the moon a little bit differently. So let's see. Here we go. We're going to do phases of the moon here. This is the next slide. The moon appears to have phases or different shapes depending on how the light from the sun shines on it. So let's take a look at this diagram here first, and then we'll do a little animation that I found that I think is pretty cool. Okay, so when we see the full face of the moon lit up with sunlight, it looks to us like a full moon. So let me just draw over here on the side. Okay. So here is, let's see. Okay, so here's the full moon, okay? Full moon. And here's the Earth. Okay, and we are on the back side of the drawing of the Earth here, okay? So here's the equator, and there's the equator on the other side. Got it? We're over here on the back, and we're looking at the full moon. Where's the sun? Well, the sun is way over here behind us. And the sunlight is shining on the moon like this, you see? Now, this is a picture that's not to scale or anything, and it's a little tough to draw this, but the sun is shining on the moon so that we see the full face of the moon lit up. That's a full moon. Okay? Now, when we're looking at the moon, let's see if I can do this. When we're looking at the moon and the position of the sun, according to us, is now over here, what happens is the sun shines on the moon, and we see just half the moon lit up. Okay? Okay? And so that's when we see this. Okay, so we have full moon. Now, where would it start? There's first quarter. Okay, so it starts at the new moon. New first. Okay, it starts at the new moon. What happens at new moon? Well, the moon is kind of like over here. The sun shines on the moon. This half half of the moon is kind of always lit up, right? And we're over here now. Let's just say we're over here. We're looking up at the moon, and we can't see the moon at all because the back side of the moon is lit up, and we're looking at the dark side, so we can't see it. The new moon. That make sense? That's cool. Isn't that cool? So the moon is always revolving around the Earth. The Earth and the moon are always revolving around the sun. So there's lots of things at play here.
Won't be the solar eclipse.
Okay, yeah, we're going to get into eclipses later. That's right. But as you can probably imagine, because there's the sun and there's the moon and the Earth rotating around, right? So look at this. At this point, there could be a shadow that's cast on the earth here. And that would be an eclipse of the sun. The moon is literally in the way. That's what an eclipse is like. Now, but we'll get into eclipses a little bit later, okay? So new moon, okay, and then a waxing crescent. So I want to talk a little bit about waxing and waning, okay? Waxing is coming on. Waxing is coming on. Think about that, okay? So the light is starting to overtake the moon. We're working towards the full moon. So waxing crescent, this is like your typical kind of, the shape of the moon and all the kid stories, right? It's like, oh, moon, you're so beautiful. It's like the crescent moon, right? So that's the waxing crescent. First quarter is like half the moon when the right side is lit up. Waxing gibbous, this is a kind of a weird little word here, but the sun is starting to overtake the moon, let's say, waxing. And gibbous is kind of like a 3/4 of what we see, maybe, right? 2/3, 3/4 of what we see is lit up. Full moon is everything. Now, waning, okay, if something is waning, that means it's sort of like starting to go away, okay? It's fading, it's waning. And so when the sunlight is starting to retreat from our perspective from the sun, then it's waning. So then we have the third quarter, waning crescent over here, okay? So I don't know if you guys realize, but you see actually the crescent facing both ways, right? Depends on the time of the month and all that sort of stuff. Okay. So here's just the animation that I wanted to show you here. So this is our view from Earth. And again, so if I pause for a second, the sun is over here on the left, and the moon is rotating around the Earth, revolving around the Earth. And this is the view that we have. So as the moon keeps revolving around the Earth, then we get a different view. And this is sort of helps explain that. Okay? I'll just let that play for a little bit. The moon might be out of view for you a bit, but yeah, so that's how we get the different phases of the moon. And in a full moon, right, we have to remember that the moon, was that it? We have to remember that the moon is actually quite a ways away from the Earth. Come on here. Okay, this is not working so well. The moon is quite a ways away from the Earth, so the Earth would not cast a shadow on the moon, very often at all. So eclipses don't happen very often at all. But this is your view. And this is your animation there.